So we have seen the time part. All right, what I mean is the following. We have played with the time part, and we have seen absorption using the second term, emission using the first term. Both are stimulated. Now we would like to discuss selection rules. Selection rules comes from the spatial integral. Okay, so we pick that up and start looking at this particular integral. So we focus on this integral. It is the electron's coordinate in between, in the middle, and then we have two atomic states, energy eigenstate 1 and 2. Okay? We also understand that both absorption and stimulation rely between two particular states, rely on the same integral. We have used Z in our derivation for simplicity. We assume the E field is polarized in the Z direction. More generally, we actually pick up the electric dipole moment, which is the charge minus E times the position vector of the electron. Therefore, more generally, we will pick up this vector in the middle. Therefore, this whole thing at the end, after integration, is a vector by itself. So it is a vector 2, 1, say. It has X, Y, Z component, and it is going to dot into the E field that will determine whether it is bright or dim or the line is missing. So all in all, we need to consider initial or two atomic states, 1, 2, and in the middle, X, Y, Z, because there are 3 components. These are the important integrals to decide whether something could happen, allowed transition or forbidden transition. I use Z assuming linearly polarized light along Z direction, but if you play with circularly polarized light, you have a plan for the E field pointing. Usually you record it XY plan, and therefore you also need these integrals. Therefore, these integrals depend on 3 things. The 2 states, atomic states, and then what is in between. So let's consider this Z, and then 2 atomic states. Think about hydrogen or any central potential. So you have this NLML, a radial and theta phi part. This is state number 1. This is state number 2 in general with all the quantum number with a prime. We need to integrate over all volume. In spherical coordinates, it is r squared sine theta dr d theta d phi. So this is the thing. And then we have a Z in between. When we turn the Z also into spherical coordinates to go with the wave functions, it is r cosine theta. So this is, by definition, what Z21 is about. 2 is on this side with a star. Okay. Now, there are angular integrals. Let's sort them out. Spherical harmonics. Spherical harmonics. We have sine theta, d theta, d phi. This is called solid angle, so d omega. But we also pick up a cosine theta from the Z. So this is the angular integrals to do. We also have the radial integral, but usually the selection rule comes from the angular integrals. So let's extract the selection rules. We have d theta, d phi. Let's consider phi integral. Remember, spherical harmonics, the phi part is EIM phi. So I have this too. And the Z, now this is Z in particular, does not carry a phi. So it's only cosine theta, no phi. So you do the phi integral, you have this. Okay, so again, ML prime must hit ML in order for this phi integral not to be 0. So for Z, this integral, we have a selection rule. This one. Therefore, delta ML is 0. So this is the first encounter of how to extract selection rules out. Understand? Okay. No more, memorizing things. It is quantum mechanics. You understand? Now, these selection rules come from linearly polarized light along Z. Therefore, you have this particular Z, you pick up cosine theta only. Okay? But don't be too happy when you hit this selection rule. There are also the theta integral that you need to worry. So let's say the phi integral is okay, not 0. Then you have to look at the theta integral. The theta integral is you have the spherical harmonics, and then let me explain. Now, you see a cosine theta, okay? Now, mathematical test number 1. Do you know P1 cosine theta is cosine theta? This is called the Legendre polynomial. Do you know this? Do you know this? Okay. Now, do you know that y Lm theta phi is related to the something called PLM cosine theta, EIM phi. This is the so-called associated Legendre polynomial. Okay, but in our case, we only did this. Okay, that is to say, when you see a cosine theta, it is like a y1 something. So that because y1 will go with p1. You understand what I'm saying? Okay. Okay. So there is some mathematical orthogonality formula for spherical harmonics. So when cosine theta provides a 1, then you need this L prime and L can only differ by 1 in order for the theta integral not to be 0. And that is the other selection rule about delta L equals plus minus 1. Okay? So that comes from the cosine theta. Now, we mentioned that for circularly polarized light, we also need x21 and y21. So let's pick up one and do the discussion on the phi integral. X is r, one factor of r, sine theta cosine phi. This is what x is in the spherical coordinates. Therefore, if you now consider the phi integral, it has two contributions. Therefore, the phi integral has to do with minus ml prime plus ml plus 1 or minus 1. When it hit this relation, is not 0. Therefore, when we consider the x and y integrals, you have this delta ml equals plus minus 1. And I think that answers one question written down here. Choi, now you understand, right? Okay, this is the plus minus 1 condition. Okay, so let me summarize. It depends on the polarization of light that you have some selection rules due to the phi integral. The simplest situation will be unpolarized light. In that case, you will have delta ml equals 0 or plus minus 1, and then this delta L equals plus minus 1 for your selection rules for electric dipole mechanism allowed transitions. That works both for absorption and emission. And it is because of this selection rules, you have such allowed transitions in the low-lying hydrogen atomic levels. So here, the arrows depict those transitions, satisfying the selection rules written down on the first line there. Okay, so the next time when you see this, for example, in chemistry or in some other places, don't worry, just quantum mechanics. So there's a question. But if I have a free electron, there's no preferred direction, but why the selection rules are different? Okay. The whole point, I think, is that you don't have a isolated hydrogen atom anymore. You have light. So the light, depending on the incident direction, so there's a k direction, therefore there's a perpendicular to k direction plan, and then there are some specific directions. Once you have to fill in. Okay. So this is the page that I just discussed. So I don't need to go through it again. I'm trying to argue cosine theta is a y1. Okay, and you use those, you can Google spherical harmonics. It will give you this 3 spherical harmonics, the product of which when they are not 0. Last point, what we are playing with is within the electric dipole mechanism. So when we say something is 0 here, it doesn't mean that transition cannot occur at all. It cannot occur within the first order electric dipole transition, meaning through one photon. First order, we have only one H prime. So basically, if you quantize the light field, it means single photon processes. So when we say forbidden, it's not absolutely forbidden. It is forbidden within our scope. The mechanism we assumed, and the theory, the level, the depth of the theory that we are using. But what we are discussing is the most important mechanism and also the most important formalism. So there may be higher order processes that could occur. Even we found this is forbidden within our level of discussion. So there could be, for example, things ignored here called two photon processes that is beyond our discussion. Earlier, I showed you some references about propping how big is the nucleus, how big is the proton. If you go into those literature, you will see that they use a highly precise spectroscopy to prop how big this size of the nucleus is so that it will influence the transition. They use 1s, 2s transition, which is forbidden within our discussion, a 1s, 3s transition, which is also forbidden, but those are two photon processes that is beyond the scope of our theory. The reason that when they try to probe the size of the nucleus, a proton, they use S state, is that only S state has a bigger wave function near the nucleus. Or the P, D, F state is 0 at the nucleus. Okay? Think about 1s. It is exponential minus R over the Bohr radius. At the Bohr radius is the highest. So that's why this experimentalists always try to probe transition using S states. But this is not electric dipole mechanism. So this is the same figure. I just want to show you that what is the so-called S series, P series, D series. Once upon a time, those were the adjectives about sharp lines, principal lines, diffuse lines, and so on. But those are historical remarks. So we have understand selection rules suddenly using time-dependent perturbation theory. We have more works to do. Let me see. I'm looking for some books. So let's extract more results from our quantum mechanical derivation. So we have worked through this and get a delta function here, right? So now I would like to make use of this result and extract something that experimentalists can refer to. It is called the rate of transition. How fast something could happen or how slow something could happen. That is called the rate of transition. Basically, it is probability per unit time. We can do it because of our previous discussion. This thing has a peak, the area under which is proportional to t. So at the end, this will be proportional to t. Divide the t through, that will give us probability per unit time. That is called the transition rate. Okay, so you have some anticipation. But before doing that, I would like to shape it into something more useful in relation to the discussion to the Einstein's theory in 1916. Now I want to make use of your E and M actually. This is the field amplitude square. So let me multiply by half epsilon 0. Now this is epsilon 0. This is bigger. This is the E field. Okay, so don't be confused. I have done nothing. I divided by 2, multiplied by 2. I multiply a epsilon 0 divided by epsilon 0. So I've done nothing. But once you have this factor, I hope that you realize that this is the energy density according to electromagnetic theory. In unit, it is energy per unit volume. So I'm rewriting the prefactor. You may wonder why. Because this shows us very clearly that it is stimulated absorption or stimulated emission. It is proportional to how strong the incident field is. This can be closely, this can be related, I think, off by a factor to the intensity of the incident light at that frequency omega. Notice that I put in a subscript omega because our discussion so far is about monochromatic incident light. It's a single omega. So all the field here is about cosine omega t. So I put an omega here. Okay. What for? Because I would like to generalize it to the more usual situation in which the incident light is not carrying only a single frequency. Usually the incident light has a narrow band of incident frequency. Therefore, let's define something in a continuum description. The capital U, which is a function of U omega d omega is the energy density of the incident light in the interval omega to omega plus d omega. Now, you have encountered such continuum description many times in previous courses, I think. For those doing statistical physics, there is something called the density of states, density of single particle states, that you use this kind of idea, all right? So notice that this U of omega has a different units from this U of subscript omega. Now, this is energy density. This product is energy density. Thereby, this thing alone is energy density divided by an angular frequency, divided by an omega. Okay? So be careful. Now, what is the idea? The idea is that we are going to consider a distribution. So I have a light source that I brought, And then my atom has a particular omega 2,1 that is E1 divided by E2, E1 minus E2 divided by H bar. Now I buy a laser that goes like something like this. Okay, so it has a distribution of frequency over this particular one that I would like to make use of. I draw it very broadly, but realistically, it could be narrower. However, that should be overlapped onto the very sharp F of omega that we discussed. Okay, so in that context, when I zoom into that very narrow omega, my laser distribution in frequency indeed look very broad. So that is the idea. So with this idea behind, think about the following situation. If I pick a frequency omega 1 that is within the range, I do the quantum mechanics for this particular omega 1, I would have gotten a A2 referring to that omega 1. What I'm saying is that this become omega 1, I get one formula. Okay? Then I have an omega 2, I get another formula. I have an omega prime, I get another formula, and so on. So this is my range. Therefore, if the incident light consists of all these different frequencies, I could add up all this A2 square to get the total effect, how this beam, narrow beam of incident light, narrow beam in frequency, this incident light induce transitions. I add up the effect of different frequencies. So let's put this idea into mathematical formula. Therefore, I can write the following. For frequencies that lies within the interval omega to omega plus d omega, I can regard them all the same as omega in this tiny range. This is the energy density. So this played the role of U of omega before, but now I'm preparing for a distribution. Okay, so that will be the contribution due to this energy density that lies within this particular tiny range. But I have a distribution. I have to add up all the components of omega. Therefore, I do a integral. I add up all the contributions. Okay, so here the first line is generalizing the previous monochromatic source into a band of incident frequency. Do you get that? The next step is very simple. Remember, we play with this f of omega, and we argue that it goes like t delta function omega minus E2 minus E1 divided by h bar. It is a delta function. Okay, so we can immediately do the integral because this is a delta function. It will force this omega to be right at this omega 2,1 because the delta function says omega must be equal to that number. Therefore, it will pick up the strength, how strong in your beam, in your narrow distribution of frequency, that particular frequency, how strong is the light. So I have that. Okay, so that very explicitly tells us that we are working with stimulated emission because this represents the strength of the stimulation. As I said, this can be easily related to the intensity. And more, this delta function has one factor of t. Area under that bump, that peak, goes like t. So we have a factor, single factor of t. So let me put all the things together. I single out the t at the end because I'm preparing to divide it through to the left-hand side. The rest are something related to the electric dipole moment, the integral between the initial final states. This is called electric dipole moment matrix element. Matrix element because I have two indices. I have two states, take any two states from the atom, do this, it is a matrix element. And then I also pick up how strong the incident field is at that particular frequency. Okay, the rest is just some constants. Therefore, well, I copy this through here, blow it up to convey the physical sense here. What are the dependents? We already discussed this, selection rule. We already discussed this. This has to do with stimulated processes. It is, you can interpret it as the intensity, how strong your incident field is, but you have to be at the right frequency due to the delta function peak you pick up. And then it is linear in time. But as the previous question posted by the student, I already explained, this time is not meant to be very long time. You don't need to worry about this growth indefinitely. This time practically maybe millisecond or second, that is already very long compared with if you have yellow color, that the time scale to compare with is 10 to the minus 14 seconds. Okay. Now, the punchline. I would like to do something that is per second, per time. So I have a time over that side on the right-hand side. Therefore, it is very easy to divide the time through, then I will get something called the rate of transition. Okay. Now, I can start with the stimulated emission expression, the 2-1 expression instead of 1-2 expression, following the whole every steps. I haven't done it here for you explicitly, but the answer is very clear. It's the same thing, only that this is 1-2 and the 2-1. But we know this square is the same for two different states. Okay. Therefore, we have the same expression. Then we can start to play with transition probability per unit time or rate. The definition is actually do a derivative with time, but the time is single out there, so just divide it through, it's okay. So I haven't done the d, I mean, you have to take a derivative d of this dt, so, but there's only one t, so divide it through, all right? So now we have some useful answers. Divided through by t, then this is called transition rate of absorption. We are really done with it, okay? Now, we have done the Z thing, and then we divide it through, we get that. But more generally, this answer is written as with a 1/3 in front and turn this into x, y, z vector integral. Now, this is to prepare for all, for example, unpolarized light. So usually the transition rate is given by this formula rather than the one that we step by step derived. A remark here, don't worry about how to go from here to there. Don't worry, because all the key physics are captured. We have stimulation. We need the frequency to be right. We know the selection rule is related to not only Z, but also XY integral between the two states. It is here. Okay, so we have all the physics. The prefractor off by 1/3. Well, we can go through step by step from 23 to 24, but I don't want to waste the time here. Now, since we know the parallelism between stimulated absorption and emission, we don't want to repeat all the steps. We can also write down the stimulated emission formula as this, okay? So let me look at it one more time. 1 to 2, I have two, 1 is lower, 2 is higher. So this is absorption. 2 to 1, this is emission, okay? The same rate. Okay, now this is important, as I already hinted at. Einstein got this before quantum mechanics was established. He used some statistical physics argument. We will do that a bit later, maybe Tuesday. So let me summarize. So far, for stimulated absorption and stimulated emission, we have derived A 1 to 2 square and A 2 to 1 square. Also, lambda, which is divided by time, okay? The rate, lambda 1 to 2 and lambda 2 to 1. We have derived it by Schrödinger quantum mechanics. And we found, provided that the light intensity U is the same, then the transition rate of stimulated absorption is the same, equal to the transition rate of stimulated emission. So that is what we know. And that is quite profound, I would say. Not so, a little bit of technique, you know, time-dependent perturbation, and then you get a lot of things out. Selection rules, rate, that, you know, one can judge whether these two states, is it good for light emission? LED, light emitting device, will that be good, right? So it is a very practical thing. So let me summarize this part. We have done the stimulated emission and stimulated absorption. You may wonder, what about spontaneous emission? Now, that is hard. That is hard within Schrödinger quantum mechanics, because if we follow the emission formula, the problem is there's nothing to stimulate it. If we set this to 0, then it said there's no spontaneous emission. And that's true within Schrödinger quantum mechanics. An eigenstate there, you don't stimulate them, it will not come down. Okay? Because it's an energy eigenstate. So the problem about spontaneous emission requires further consideration. The way we will approach this part, spontaneous emission, is to find a detour. Okay, so we will find a detour at the end, we will get another quantum mechanical expression for spontaneous emission. The way we will go is, we rewind the clock back to Einstein's time, 1916. He did a statistical physics argument for the Planck's black body formula. At that time, everybody knows stimulated absorption will occur, spontaneous emission will occur. That was a common sense at that time. But Einstein found that he needed to introduce a funny, a mysterious stimulated emission process in order to get the right Planck's formula. That's why many credit Einstein for inventing or discovering stimulated emission. And therefore, even many said Einstein discovered the laser. But I think it is an overstatement, because laser was eventually built only in the 1960s, 50 years, 40-something years after Einstein's work. So after we did the Einstein discussion, then we can relate spontaneous emission to stimulated emission. Because we have the answer for stimulated emission, therefore we can copy the result to spontaneous emission. Okay, so we can do it, but need a little bit of work. The third point is that these few equations, this one, or this one, or this one, are often called Fermi golden rules. They are special forms of Fermi golden rules. Fermi golden rules is a key answer in time-dependent perturbation theory regarding not from one state to another, but with a something like a band of incident light, or from an initial state to a group of final state. But it's very funny. Actually, the answers were first derived by Dirac, but somehow Fermi's name was attached to it. And what we haven't done, but you can easily do it, is what if I have a group of state 2 instead of a single state 2? So the idea is the same. You introduce a density of state for the final, for the state number 2, and then you generalize the formula from a single state 2 to a group of state 2 by introducing an integral over the density of state 2. Okay. Final hint, we have lambda being a transition rate, which is 1 over time. Therefore, if I flip lambda, it is something like a time. So it may be related to some, say that experimentalists refer to the lifetime. And it is true. What we got so far, if we flip it, it's not exactly the lifetime, but it is proportional to the lifetime. For the following reason. The lifetime of an excited state is defined to be due to spontaneous emission, not due to stimulated emission. We had the formula for stimulated emission. But after we did the Einstein discussion and come back with the spontaneous emission formula, we see that the formula carry all the factors, only that there is an additional omega factor appearing here. There will be an omega 3, omega to the 3rd power here. But then when we flip this, we flip the whole thing, at the end, we have the lifetime of an excited state. And that is a measurable quantity. Okay? So I think I have to stop here due to time. So next time we will forget about quantum mechanics for a while and then did what Einstein proposed before quantum mechanics. Some very insightful, very simple thing to do if you know a little bit of statistical physics. Okay, so I will stop here today. If you have questions, please ask.